Welcome back. Now that we've tackled the ideas of continuity and limits, we're ready to turn our attention back to the tangent line problem. Remember back in chapter 1, the tangent line problem was for us to, for any function, find the equation of a tangent line at a point. The idea that we were working with was that we would start with the easier problem, which is coming up with the equation of a secant line, something where the line crosses through the graph in two places. Once we had our secant line, we would turn that into a tangent line by letting the 2 points get closer and closer and closer to each other until the distance between our 2 points was essentially 0. So let's get ourselves started on this journey. So I've got a generic function f of x, that's my little black curve that I've drawn here, and I'm interested in finding a tangent line at the point when x is equal to c. So if f of x is my function, then at the point when x is c, the y value would be f of c. And so this gives me 1 point on the curve, c and f of c. So what I'm interested in is letting my 2 points get as close to each other as possible. So I'm going to introduce delta x as meaning the distance between my two x values. So if my first point is at c, then my second point will be delta x units away from c. Or in other words, my second point will have an x-coordinate of c plus delta x. And of course, if this is my x value, then putting it into f of x will give me my y value. So c plus delta x and f of c plus delta x. That's my second point. So I've got myself my 2 points, and of course, if I wanted to find the slope of that secant line, I know that it's just the change in the y values divided by the change in the x values. So I've done my y value minus my other y value over my x value minus the other x value. And that simplifies to give me this, f of c plus delta x minus f of c all over delta x. So for whatever c that I've chosen, for any delta x that I look at, this little formula will give me the slope of the secant line, passing through when x is c and when x is c plus delta x. So if you're having flashbacks to your pre-calculus class at this point, you really should, because that little expression that we just looked at was essentially the difference quotient. So a couple of things just to mention about this difference quotient. Number one, in my drawing, I drew it so that delta x, that distance, was a positive distance, and so that my second point was to the right of the first one. But I could have just as easily had my second point be somewhere to the left. In other words, delta x would have been a negative number. And I could do the same sort of an idea of start with a secant line and then let my 2 points get as close to each other as possible. The other part to address here is the getting as close to 0 as possible. That's, of course, using limits. If we're looking at taking our 2 points and letting delta x get as close to 0 as possible, what we're doing is looking at the limit for our difference quotient as delta x approaches 0. So that's what we're doing here. We're starting off with a difference quotient, which essentially gives us the slope of our secant line, and then we turn it into the slope of our tangent line by letting our delta x get as close to 0 as possible, and we do that with limits. So now we can officially define things. If we're interested in some function f of x, and it has to be defined on an open interval containing our point c. So in other words, we're talking about some interval of real numbers going from a to b, and somewhere inside that interval, c is inside. So that means c is not the end point of some interval that we're interested in. There has to be some function happening on the left of c as well as some function happening on the right of c. So that's going to have some consequences for us later on. So first thing, we've got our function. It's defined on an open interval, and C is inside that interval. And if I'm looking for my line passing through C, f of C, with my slope, that is the limit as delta x approaches 0 of my difference quotient, then as long as that limit exists, then what I've got will be the tangent line. In other words, this limit that I've just found, that will be the slope of my graph or the slope of my tangent line. So actually it's two things really for the price of one. When I'm finding the slope of my tangent line, I'm also finding the slope of f of x. I'm finding how the original function is changing. Consequence to mention that we said back here at the beginning that our point needs to be defined on an open interval. So in other words, there needs to be some function happening to the left of the point and some function happening to the right of the point. That means if you were interested in something like our square rooting function, y equals square root of x, that function is only defined starting at 0 and going onward to the right. So if you were interested in a tangent line when x is 0, you'd run into a problem because there is no graph happening on the left of 0. The graph happens to begin at x is equal to 0. So you could find a tangent line at 0.1 or 0.2 or 0.3, any small value close to 0. Yes, a tangent line will exist because there is some graph happening on the left and on the right of those points. But at 0, there is no graph happening to the left of it, which means you will not be able to find a tangent line to square root of x when x is 0. Okay, so we want to find the equation of the tangent line to this function, f of x equals x squared plus x minus 6 at x is equal to 2. So a couple of things, of course. If we're looking for the equation of a tangent line, we're going to need two things. Number one, we're going to need to find our slope. And number two, we're going to need to know what our point is. And I'll do the point first because that's actually the easiest part. For the point, we already know what the x-coordinate is. The x-coordinate is 2, and we just need to know what the y-coordinate is. And the y-coordinate I find by putting 2 into my original function. And so a little bit of cleaning up, and I find that my y value is 0. So the point that we're talking about is the point 2, 0. So I've got one of my little things already accomplished. The second thing that I need to find, which is the slope of my tangent line, for that I'm going to need to find my slope by using limits. My slope is the limit as delta x approaches 0 of f of 2 plus delta x minus f of 2 all over delta x. Now, conveniently enough, we've actually already figured out what f of 2 is. We did that a little earlier. And remember, to find f of 2, we just put 2 into our original function, replaced all of the x's with 2's, and then cleaned things up, and we wound up with a value of 0. When I'm finding f of 2 plus delta x, I'll do the same sort of an idea. I'll replace all the x's in the original function with 2 plus delta x. So I'll have 2 plus delta x squared plus 2 plus delta x plus 6. All of that is f of 2 plus delta x. F of 2, we figured out what that was earlier. That was just 0. And there we go. So now at this point, and this is going to be a running theme, so again, if you dealt with difference quotients in your pre-calculus course, and hopefully you did, if you haven't, and if this is new to you, then you'll notice that there's going to be always some algebra that needs to happen at this point before we can start evaluating our limit. In this case, what I'm going to need to do is start expanding things, cleaning things up, and then I'll be able to hopefully let my delta x be getting closer and closer to 0. One thing, of course, that you'll notice as I'm doing for each and every line, as I'm writing down my next line, until I actually evaluate my limit, I'm going to have to write limit delta x approaches 0. So right now I haven't let delta x approach anything, so I still have to keep writing limit delta x approaches 0 on each and every line. So let's clean this up. And so if I expand the top, 2 plus delta x, when I square the whole thing out, I'll have 4 plus 4 times delta x plus delta x squared. And I've got another 2 plus a delta x. And I just realized I copied my function down wrong. So just to scroll back up for anyone who didn't notice my error was I was trying to work from memory as to what f of x was, and I misremembered it. It's x squared plus x minus 6. So if you noticed that, good for you. If you didn't notice that, now we do. So there we go. We'll pick up from where we left off and continue cleaning things up. So where were we? We had 2 plus delta x squared. I did all that. I had 2 plus delta x. I've got that. I need my minus 6. And of course, minus 0. And now the next thing that I'm going to do is just a little bit of cleaning up. You'll notice here that I have the 4 and the plus 2 and the minus 6. All that adds up to 0, and I've got a 0 and a minus a 0, so really all of those are going to be gone. The only thing that's going to be left in my numerator will be the 4 delta x, the delta x squared, and the other delta x. So in other words, if I were to simplify that, I'd have 5 delta x plus delta x squared. So I'm going to continue this on the next page. So limit delta x approaches 0, 5 delta x plus delta x squared all over delta x. Right now, if we're thinking about trying to evaluate this, if I put in 0 for delta x, then I would have 0 in the numerator and 0 in the denominator. That's an indeterminate form, so can't just start substituting 0 in, but what I can say is I notice that delta x factors out of the numerator, leaving 5 plus delta x behind, and that I'm able to cancel a delta x from the numerator with 1 from the denominator. And now I have something that's no longer indeterminate. I look at limit of delta x approaches 0 of 5 plus delta x, and for sure I can let delta x go to 0 now, and I'll be left with 5 plus 0, which is just 5. Okay, so one thing you'll notice already is this problem is a little bit on the longer side. I haven't even finished my problem yet. I've done some of my side work, but the original question wasn't just to find a slope. The original question was to find the equation of the tangent line. So all of the work that I've just done now with my difference quotient and with limits, that was just finding my slope. And now I'll take my slope that I've just found, which is 5, and my point which I have, which is 2, 0, and now I'm going to create the equation of my tangent line. So we have a tangent line with the slope being 5 at the point 2, 0, and I'm going to use my slope point form. Y minus the y coordinate equals slope times x minus the x coordinate. And then just a little bit of cleaning up, and we're finished. So y equals 5x minus 10. That is the equation of my tangent line to my curve f of x equals x squared plus x minus 6. One thing that I probably would want to mention to everybody before I continue on is how did I even know that this limit should exist? How did I even know that I'd be able to find a tangent line? if we're going back to what we've said already in the previous slide, whatever point we're looking at, if we're looking for a tangent line there, it needs to be inside of some open interval containing that point where our function is defined. And conveniently enough, this function is a polynomial function. We know it's defined for all x's. So at x equals 2, there's a little bit of the function that's to the right of it, and there's certainly some more function that's to the left of it. So 2 is inside of an open interval where f is defined. So that meant that we were already in a good position to go ahead and try to find our slope of our tangent line.